Welcome to this lecture where we will discuss mass balances for the technical feasibility analysis. Once the conceptual process designs are completed, we can proceed to the quantitative assessment and comparative analysis. This is step 4, and this can be done at different levels. First, we need to check the technical feasibility and make sure that all process units perform as expected. It means the design should be reliable. Then we can continue with the economic, environmental, social, and integrated sustainability assessment, which we will cover later this week. For the technical feasibility analysis, we will focus on mass balances. Other aspects of the separation recipe, as you may recall it from previous weeks, are out of the scope of this lecture. However, the accuracy of the mass balances will depend on the right application of concepts and principles according to the process phenomena occurring in each processing unit. Let's take a look at the fermentation unit. We can do mass balances in the broth, where there is biomass, substrates, including dissolved oxygen, products, and of course, water. We can do the same around the gas phase. However, only the combined balances can truly describe the mass flows going through the fermentation unit. Additionally, the operation mode, either batch, fed batch, or continuous, will also affect the mass balances. The starting point for the mass balances is the law of mass conservation, which states that mass is neither created nor destroyed in a chemical reaction. And we can apply it to the total mass balances interacting with a specific process unit, where we can say that what goes into the system minus what comes out of the system is equal to the amount of mass accumulated within the system. We can also apply it to individual components, but in this case we have an additional term which is the production of products, and this is negative for reactants. These balances are valid in a molar and mass unit. As a recommendation, always double check the unit's consistency. This mistake is more frequent than expected. Now, the type of operation leads to systems that are either steady state, which is the case of the chemostat, and non-steady state for batch or fed batch systems, and mass balances for each case are different. Let's take a look at the 3 operation modes. In a batch system, the substrate is fed before the process starts. Then the close operation takes place and no mass is fed or removed during the process. Finally, the products are removed once the process is finished. This is a non-steady state system where process variables like volume, titers, or reaction rates can change during the process. For the chemostat, the inflows are continuously fed to the system and the outflows are continuously removed from the system. This is a steady state operation, and in this case the process variables do not change along the process. It is important to mention that continuous fermentation is hardly ever used in an industrial scale. The fed batch process has elements of the batch and continuous systems, and we could say that it is just a point in between. In this case, part of the substrate is continuously fed to the system, or part of the products are continuously removed from the system. This is again a non-steady state system where process variables do change along the process. The different operation modes lead to different types of mass balances: integral balances and differential balances. Integral balances are for non-steady state processes, and they capture the dynamic behavior of the system. In this case, designers should be able to know what happens between 2 instants of time. For example, how much product is produced from the start to the end of the process, or how much substrate is needed in total, or what is the reaction volume at the end of the process. These balances account for an accumulated amount between 2 instants of time. Differential balances are for the steady state system, like the chemostat. In this case, designers should know what is happening in the process in an instant of time. For example, how much product is being produced now, or how much substrate is being consumed, or how much heat should be supplied or removed in a continuous manner. These balances indicate the rate of changes occurring in the process in an instant of time. Now, with this information, we can check the mass balances for the fermenter, and we can apply the general mass balances equation by component in a molar basis. We can also express the individual molar flows in terms of the molar concentrations and the fermentation volume. And then we obtain the same expression for mass balances as in week 2, where R stands for molar rate of conversion of each component, and it depends on the mass-specific rates, biomass titer, and fermentation volume. Then we finally have the generic equation for mass balances by components in the fermenter, which is expressed in a molar basis. Now you can reproduce the mass balances for all components as in week 2. When doing mass balances, we can apply some rules to simplify our calculations. For example, in all cases for global balances, the production term of the general balances is equal to 0. The same applies to balances by components for non-reactive species. Then we have a simplified version of the general balances. In the case of steady-state systems, there is no accumulation of any species at any point. And for these systems that combine non-reactive species and steady state, we get the simplest expression of the general balances, which is often applicable to downstream processes using non-reactive species in steady state. This gives the conceptual basis for mass balances considering different operation modes, which you can apply to the different processing units of your process design. This is all by now. Thank you for your attention, and see you in the next lecture.